Okay, so moving on to our first distinguished speaker, we have Mr. Peter Morgan. Peter Morgan has a 1978 Oxford undergraduate degree in mathematics and worked as a computer programmer, then took a 1993 Durham master's degree in particle physics. Since then, he has worked to understand the relationship between quantum fields and classical random fields. He participated in seminars in philosophy of physics at the London School of Economics and in Oxford until 2004, since when he has held a lab associate position in the physics department at Yale University. 3 recent papers in Physica Scripta, Annals of Physics, and a Journal of Physics A have developed a quantum and random field approach to measurement theory that clarifies the classical quantum transition. Without much further ado, ladies and gentlemen, I'll welcome Mr. Peter Morgan. Sir?
So, thank you, and confirm as traditional whether you can hear me?
Yes, we can hear you audibly.
Excellent. So I'll just drop into the chat a link to the PDF for the talk on Dropbox if anyone wishes to look at that. So rather humbling to follow that great talk, but I will do my best. Nonetheless, it will not be anywhere near so practical. This will be really quite a theoretical talk. So to leap straight in, it's a common story that's told that quantum mechanics is incomplete. And so people try to add to quantum mechanics things like hidden variables or dynamical collapse or such like, to try to make quantum mechanics be more like classical mechanics. But I want to play a different game. I want to play a game in which I take quantum mechanics to be complete, in which indeed all your quantum optics textbooks and all your other textbooks about quantum mechanics will be completely unchanged by anything I'll say today. But I also want to say that it seems to me that classical mechanics itself is incomplete. It's the opposite way around, because of all the no-go theorems that prove it's not as good as quantum mechanics. And so I'm going to discuss what we can add to classical mechanics to give us what I'm going to call CM+, so it can describe whatever we can describe with quantum mechanics. And then nanotechnology, or indeed any experiment, is just what it is. How you describe it makes no difference once you've built it. But on the other hand, how you describe an experiment in 2 different ways, one of those ways may suggest that a new experiment is a good thing to do, whereas the other one is more reserved, doesn't think it's actually wants to do a different experiment. And so it does make a difference if you have 2 different ways of looking at, of doing the calculations that will tell you what an experiment will do. So the hot take here is, we don't have to think that there is any transition between quantum and classical. We can describe it either way, depending on which is most convenient. But we can think in terms of transitions if we want to do so, because, well, as I've just said, all the textbooks will remain unchanged. So this is the outline for the talk. I'm going to talk very much in terms of signal analysis. I'm not going to mention particles hardly at all. And I find this makes a great difference to how experiments look. Because we work with devices on which we have a noisy signal, and every now and then we see an event happen. We record the time at which that event happens, which becomes our data, and then we analyze that data. So to really push home what this looks like, I'm going to look at the violation of Bell inequalities from a signal analysis and field theoretic point of view. As I say, there won't be any particles in this. So this will suggest that one of the main things we should add is non-commutativity, measurement incompatibility into classical mechanics. And the other thing I'll say we need to add is the idea of quantum noise as something different from thermal noise, and yet nonetheless classical, just noise. So again, applying signal analysis, but also thinking in terms of probability theory, we'll be able to apply what we've learned about classical mechanics when we've added non-commutativity to the measurement problem and in terms of joint probabilities. And then also that will give us some sort of key into how we can think about measurement incompatibility as purely something quite classically understandable, intervention and causality. Now, the last part of the talk will be quite technical. I want to show you how, if we think in terms of signal analysis, we actually could do quantum field theory in a rather natural sort of way. It's not so complicated if you think in terms of modulation and measurement instead of the ways in which quantum field theory is taught in textbooks. And indeed, I think a signal analysis approach can actually help us understand interacting quantum fields. And for anyone who knows their quantum field theory, there's the renormalization is a serious mathematical problem, at least I take it to be so, and I'll show you how we can do something about that. So this is my schematic of what I think an experiment looks like. Obviously rather crude, in which an experimental apparatus contains whatever it is it does contain. And around whatever it is, there are many devices, and they output signals, which then go through hardware, which produces the digital data stream. Yes, go ahead.
Excuse me, Peter. Perhaps you forgot to share your screen.
Oh, I did. Thank you. That's too late.
Yes, that's okay.
And share.
Thank you.
Yeah, that will be much better. I'm going to go back a tiny bit. There's the beginning. There's the first slide. And as I say, the hot take is we don't have to think there's a transition between quantum and classical, but we can. I'm not saying you can't at all, but I'm going to skip. This is the second slide, talking about devices and how the signals, you have events happen. And then finally, you record the event times as data. And that I'm going to talk about in terms of violation of spell inequalities, signal analysis, and field theory. And classical mechanics, I'm going to say we can add non-commutativity, and we can add quantum noise. And measurement problem, we can think of in terms of joint probabilities, and particularly in terms of signal analysis. And for measurement incompatibility, we can think of that in a very natural classical way, I'm going to argue at least, in terms of an intervention, changing settings on experiments. And I'll explain that, obviously. And for quantum field theory, again, I'm going to try to talk in terms of signal analysis and talk about renormalization. Okay, back to where I should have been a few minutes ago. Right. So an experiment, we have the schematic in which we have the experiment. The apparatus contains whatever it is it contains and surrounds that by many devices. And each of those devices outputs a signal that then hardware converts into a digital data stream, which is then recorded. Then we analyze that. We write a supplementary information in a paper that describes the experiment and its data well enough that we can hope that someone else would be able to produce the same experiment and its results. So for quantum mechanics, we have measurements, which we might index just as measurement 1, 2, 3, 4. And of course, that's not enough. You need something that tells you, that describes how you did each of those measurements. And that should be enough, as I said in the previous slide, for an experiment to reproduce those experiment measurement results. So instead of writing M1 and having a separate description, we can write M with different descriptions. Now, in quantum field theory, to start the process of trying to make it seem like a fairly simple sort of thing when it really is, perhaps it isn't, measurement operators are not point-like. It's important to note that even though we talk about quantum fields as operator-valued distributions, we always, if we're being at all careful, should smear them with what are called test functions, and what in signal analysis is called a window function. And that tells you how a measurement is different from being point-like. It tells you whether it's very small, very large area that is being reported about when you perform a particular measurement. And we must introduce quantum field theory because quantum noise is different from thermal noise. And in any case, we are working with signal analysis in which I'm going to argue, is already a field theory in 1 plus no spatial dimensions. So for quantum field theory, we have what I'm going to call an F measurement, commutes with a G measurement so that we can produce the probabilities easily if the two functions are causally or space-like separated. But I'm also going to introduce something that is relatively new, and that is what I'm going to call a quantum non-diminution field theory. All that means is that a QND F measurement we can always produce a probability distribution for it and for a different measurement. So we can always produce joint measurements for those. And that looks very, very classical, and that indeed will look very much like CM+. And I'll show you how later in the talk, how we can produce a quantum optics isomorphism to a quantum non-demolition optics, which we can think of as really much more classical than quantum optics itself. So to think about a violation of Abel inequalities in terms of fields and signals, and this particular schematic is from an experiment from the mid-1990s from by Gregor Wies, in which one of the nice things from my point of view is that he talks about the central apparatus pumping whatever it is that's happening within the apparatus. He doesn't talk about sending particles down the line. So from my point of view, we modulate whatever it is that is contained by the apparatus. Now, Alice and Bob both have two avalanche photodiodes. They have an electro-optic modulator, they have a random bit generator, and they have a clock just here. And so there are 4 signals, just as I had in my schematic, going into hardware, and out of that hardware comes a recorded time and which of the APDs the event happened on, and what the setting was to the electro-optic modulator at the time. And of course, this compressed data here really tells us nothing about the signals coming out of these 2 APD devices. So just to clarify how I think about an APD, an avalanche photodiode, these things are very exotic materials. They're processed in exotic ways. They're surrounded by exotic electronics. They're quite complicated objects. An APD mostly, I'll say, burbles along while it interacts with its surroundings, but sometimes it gets cross at the world, and hence we have an event happens. And that's more interesting than using devices that do nothing. A rock would not give us any events, and so we don't use them. An APD's electronics calms it down so it can burble again, so we can get new events, and then we can start to do statistics because there are many events. An APD sometimes gets cross with itself, even if we put it in a dark room. There's what's called, as I'm sure many of you know, the dark rate or the dark statistics. But if we change what's in the room, if we introduce another light source, if we introduce other APDs, if we introduce mirrors and so on, then the statistics change, and we can investigate systematically what might be happening in the room that we've got the APD in. Now, an APD, I suggest, tells a story even when it's just burbling along. And indeed, you can find an experiment in Nature 2019 in which the electronics even looks at the signal here, realizes an event is about to happen, and stops the event happening. I think it's important to keep track of what the range of frequency scales is involved here. The optical to the human is 15 orders of magnitude. We're looking to record things at 9 orders of magnitude separation from the stuff we really would like to know something about. It would be better, I suggest, if we could store much more data and really record the electronic signal and do post-analysis of that instead of doing post-analysis just of event times. But in the 1990s, Gregor just stored event times, and these are the measurement results he got on one particular 10-second long run, in which Alice saw 400,000 APD events. And for those 400,000 events, 15,000 of them, every single one of which is displayed here, has also an event is recorded by Bob within 3 nanoseconds. This is 6 nanoseconds wide, 10 seconds long, huge difference in scale. And when they both record an event within 3 nanoseconds, the majority on the color scheme I've used are green or yellow. And that means there are very few in this along the diagonal up here in the red, or in the lower diagonal in the blue, but the yellows and greens really happen a lot. So if we turn that around by 90 degrees and take slices, vertical slices through these, then we can produce these 16 histograms for those 15,000 events. And we can produce these 16 numbers as just adding up the numbers in each of these histogram slices. Those 16 numbers, we feed into what is basically the standard calculation that results in the violation of the Bell inequalities 2.714 here. So for this, we've taken this entirely classical data, we have put it through an entirely classical algorithm. We produced the number 2.714, for which classical mechanics throws up its hands and says, I cannot do this. This is not okay. So what's happened? If we just transformed the recorded experimental data in an innocuous way, then I suppose we could have used commutative algebras to model those algorithms. But in quantum mechanics, we use non-commuting operators to model the violation of the Bell inequalities. And this is something you'll find in the literature from around about 1980 onwards. But in classical mechanics, as usual, we don't have non-commuting operators. So I suggest without non-commutativity, classical mechanics is computationally incomplete. So the question to me is, how can we add non-commutativity to classical mechanics? And in 2 slides' time, I'm going to show you how we can. It's remarkably natural, to be honest. Now, all of this is about non-commutation, about non-commutativity. Of course, if you look at the Bell inequalities literature, you'll see a lot about non-locality. But to skip quickly through this, if you have a low electro-optic modulator rate, then that won't probe non-locality, but you'll still see the violation of the Bell inequalities. So in some sense, non-locality and non-commutativity are rather separate issues. On the other hand, I don't want to minimize this too much, because for quantum fields, microcausality associates non-commutativity very much with only a time-like separation. Now, finally, I actually don't care much about non-locality, and that's because I think of quantum mechanics and quantum field theory as being much more like thermodynamics than like statistical mechanics. And for thermodynamics, even in the 19th century, you're working with the heat equation and similar equations, which depend on boundary conditions. And that's what we would expect if we don't talk about sending particles through the apparatus, if we instead think about the apparatus containing something which is more like a field. So in order to show you the difference between classical mechanics and quantum mechanics in a relatively clear way, I'm first of all going to show you something that you can find in the literature, algebraic quantum mechanics, in which we say there are measurements, M1, M2, M3, we can add them, we can multiply them, in which linear operators correspond to random variables. The spectrum for a linear operator corresponds to the sample space for the random variables. So this is very much ordinary probability theory, so long as it's commutative, in which case we say it's classical mechanics. But if the algebra is non-commutative, then we say it's a generalized probability theory, and we say that that is essentially quantum mechanics. And I'll assume that we have basically a straightforward algebra with these kinds of conditions satisfied. Now, that doesn't tell us anything about expected measurement results. So what we introduced to tell us what the expected value will be for a particular measurement, M1, is what we call a state or a statistical state. And we can do that for sums and for products. We can also discover from the theory what we expect the moments of the probability distributions to be, and we can even write in this very compact form what a probability distribution will look like using the Dirac delta distribution for the measurement M1. Now, the next piece is we can also take the Fourier transform of that probability distribution and get this construction here, and in a very engineering kind of way, I'm going to use J because when I use a Fourier transform, I always think I should use J for that rather than to use I, as a mathematician would almost always do. So the state satisfies 4 standard conditions, basically. And these conditions become standard because they bring us straight to the Hilbert space and essentially the structure of quantum mechanics as we usually have it. And in terms of probabilities, what we require is that probabilities are positive. Probabilities are normalized to 1 when we add them all up. They're real valued, and also we can add them up. And von Neumann linearity says that even if the operators A and B do not commute, even so, we do have this linearity is satisfied. So we can also use these measurement operators to modulate the state, so that this construction here also satisfies the rules required for it to be a state. And that allows us to use what's called the Gelfand-Naimark-Siegel construction of a Hilbert space. And as I say, that puts us into quantum mechanics, more or less. So the GNS construction also lets us write a state using a vector as a bra and a ket surrounding a measurement operator, and similarly for the modulated states. So how does classical mechanics fit into this? Classical mechanics has three binary operations acting on an algebra of functions on phase space. That's how it's very often presented. There's addition, there's multiplication, but there's also the Poisson bracket. We can make, and that really is not anything like the algebra that we had on the previous slide, where there are just two binary operations, but we can make there be just two binary operations by introducing what I'm calling multiply by W, where we just define YW to be multiplication by W. And Poisson by W just uses the Poisson bracket in just the same way to give us a Z operator, Poisson by W. And a familiar example for that is Poisson by the Hamiltonian function, which gives us a generator of time evolution, which is called the Liouvillean operator. So that gives us a transformation. And indeed, the point about the Poisson bracket from this point of view is that it gives us many, many transformations. And those transformations do not commute with the multiplication. And so we end up with a non-commutative algebra with addition and composition. So this now does look like the way we have for quantum mechanics. And so I'm going to suggest, and I certainly now have taken this very much to heart, we can use both the Ys and the Zs of a more powerful CM+. We don't have to use quantization. We don't have to use the correspondence principle to go backwards and forwards between classical and quantum, because we have an algebraic measurement theory that's exactly the same as that of quantum mechanics. There's a lot we can describe just with what I've described here so far. So that's very abstract. For the classical simple harmonic oscillator, the Poisson bracket is as simple as it comes. It's this biderivation, as we can call it. Multiplication is just multiplication. Poisson by P is just the derivative with respect to Q. And the same for Poisson by Q. Gives us a derivative with respect to P with the opposite sign. And that gives us these commutation relations, non-trivial, and indeed the Heisenberg group without the complex structure. And we have for the Hamiltonian function this positive multiplication. And for the Liouvillean operator, we have this derivation, excuse me. So that doesn't tell us any measurement results we would expect. The way I'm going to make contact with quantum mechanics as quickly as it can be done, really, is by introducing the Gibbs thermal state at a temperature KT, and I'm going to introduce it in the Fourier transform way. So this is the Fourier transform of a probability distribution for the YQ and YP observables. And so that has a noise that has an amplitude given by KT. And we want to extend that to also give us the probability distribution for the Z operators. And because this is the Heisenberg's algebra, there's actually essentially only one way to do this, which is to introduce raising and lowering operators with a constant KT instead of H bar, and to say that the lowering operators annihilate the thermal vector state. With that, we can construct modulated non-equilibrium states, just as we do in quantum field theory, just like this, and hence we can construct a Hilbert space of states that are constructed from the thermal state. So instead of trying to map classical Q and P to quantum Q and P, which was never going to work, we can instead map Q and J partially Q as an isomorphism to a quantum mechanical Q and P, and the same for P and J partially P. But crucially here, KT is not H bar. This is not quantum mechanics because we've not got H bar in here yet. But I do point out that this is, in some sense, an irreducible noise, because the Gibbs state assumes there's a heat bath surrounding it, assumes there's an interaction of some kind with that heat bath, but the Gibbs state makes no description of that. It just says whatever the heat bath is, whatever the interaction is, we don't care, we don't know, we can't even find out unless we do something extra. So that is the sense in which the Gibbs state is also an irreducible noise, just as we have in quantum mechanics. So what is the difference between quantum and thermal noise? First of all, the units are different. H bar has units action, KT has units energy, so there's a dimensional difference. where we have to go, I think, to realize what the really fundamental theoretical difference is to look at quantum field theory, where the quantum vacuum, where there's quantum noise, is Poincare invariant, but thermal noise is not. And so this difference of symmetry properties, which is why I take this to be, in some sense, fundamental, we can use that in classical mechanics plus, quite straightforwardly. And if we do that, then we find that h bar is just an amplitude of Poincare invariant noise, and kT is an amplitude of thermal noise, and they're quite different. It's kind of like the difference between red noise and blue noise in signal analysis. So this gives us a new reason to think we must work with field theories, because we can't define the Lorentz group in just 1 plus 0 dimensions. We need 1 plus 1 at least. And so we have to go beyond the signal analysis of 1 plus 0 dimensions. Now, if you are thinking in terms of classical mechanics, that's a big step. But if you're thinking in terms of signal analysis, it's not as big step. This is really quite a small step even. And finally, h bar to 0 is usually in the literature. You'll see it talked about as a classical approximation. But in this perspective, from CI plus point of view, it's actually just a mean field approximation. Okay, the final slide about classical mechanics, also important, is that the generator of the Hermitian generator of evolution, of time-like evolution, is not a positive operator. And that contrasts absolutely with the mathematics of the Hamiltonian operator in quantum mechanics, the Hermitian generator of evolutions in that case, which is bounded below. And that results in analytic properties that no mathematician is going to want to give up. And indeed, I don't want them to give up. I think it's crucial to keep that as something exclusive to quantum mechanics. So we can say that CM plus includes non-commutativity. It includes quantum noise. However, analyticity is reserved to quantum mechanics so that we have these two things, CM plus and quantum mechanics, and we can model things both ways and see how they differ and see what we can learn about a system by thinking in both ways. Now, non-commutativity and quantum noise together ensures that the measurement theory is exactly the same for CM plus and quantum mechanics. It's just the dynamics is described rather differently. So we have this CM plus and we have the quantum mechanics, and they give us a way of thinking about the measurement problem. If we have two measurements A and B, which have two different sample spaces, and we describe them in using projection operators in this way, this is very standard, then if we have just a single measurement with a state vector psi, the probability for each of the eigenvalues is given by psi bracketed around the projection operators respectively. But if we do two measurements, what we say is that after the A measurement, the state collapses to the proper state psi m, which is just constructed by using the projection operator pm. And we normalize that state vector. Then we measure B in that state. So we obtain the result alpha m followed by beta n. That gives us a conditional probability, which is just the new state bracketed around the B measurement projection operators, which gives us this expression. So the joint probability is that is given just by this straightforward, much neater equation. So we have this. We can use these positive operators to generate joint probabilities for the result here. So instead of collapse affecting a state, we can take collapse to affect the next measurement. This is so straightforward that I'm embarrassed to say it almost, but you don't see it said in the literature very often at all. But if we do this, if we think in terms of collapse just gives us joint probabilities, that is something which we can then say, well, we'll construct collapse product, a measurement A collapse B that has this sample space, and we can do that even if A and B do not commute. But since we do have a joint probability, that's something we do typically think of as rather classical. And indeed, we can use commuting operators A prime and B prime and a different state vector psi prime in a bigger Hilbert space, and that gives us the freedom to construct this, which gives us the same result as we got from the expression which we used collapse for. So there's actually a mathematics for this, the Neumark dilation theorem, which allows us to construct a measurement AB that is the same as A collapse B in a larger Hilbert space. And this is an alternative to using decoherence. And I think it's much better, to be honest, as a way of thinking about what happens when we do a measurement. So we can think of what we just constructed as a super Heisenberg picture. And I say that because the Schrödinger picture applies both unitary evolution and collapse to the state, whereas the Heisenberg picture applies unitary evolution to measurements, but applies collapse to the state. So if we go one step further and apply both of those to measurements only, and the state stays unchanged, then we have the super Heisenberg picture. But if we focus on the classicality of this, and that the fact that for Bohr, measurements affect other measurements, this is something very, very well known in the history of physics, then we could call it the Bohr picture. And I find this very unifying in some sense. We really can bring together a lot of different perspectives by saying we'll work with the super Heisenberg picture when we feel it's appropriate. We can focus on the commutativity, in which case we can call it something else, or we can focus on the fact that it's not collapse, in which case we can call it the Everett picture. Or if we're feeling a little excitable, we can focus on the classicality and wonder whether Einstein would have been content with a Poincare invariant noise on top of that. If he is, then I would feel perfectly comfortable calling it the Einstein picture and feel that he wouldn't be rolling in his grave, at least. So there's a peculiarity about this, and that is that this collapse product, every way I've found of doing this, and indeed I think it's intrinsic, is not an associative operation. And so we have to decide what order we're going to apply those collapses in. And we're going to want to do that many, many times if we're going to do signal analysis, which in nanotechnology, I'm sorry, I have tried very hard to think in terms that might bring this back to nanotechnology, but nonetheless, it's something that is not second nature to me, whereas the mathematics you're seeing here is. So when we have many measurements, we could just use ordinary quantum mechanics with collapses in between and in a very carefully organized pattern of collapses. But we could also just use lots and lots of commuting operators, just as we did on the previous slides, in what we call the super Heisenberg picture or the quantum non-demolition picture. Both of them give us the same joint probability. Obviously, that's the aim. We want to get the same predictions out of the two different systems. And we know we can compute autocorrelations in signal analysis, so joint measurements of time-light separation do happen. Now, what I'm saying here is that collapse is not only or necessarily a dynamical process. We can model it as a dynamical process. None of this makes the mathematics of the dynamical collapse interpretations wrong. It still is perfectly workable mathematics. But we can also just take it to be probability theory and a rather extended probability theory, and we can make more sense of it in this way, I think. At least I feel that I can. So there's a necessary trade-off here. Quantum mechanics is rather good for incompatible measurements because it has non-commutativity really baked into it from the beginning, but then it has to use collapse when it wants to construct joint measurements. Whereas classical mechanics is rather good for joint measurements because we have commutativity is baked into it from the beginning until we introduce the Poisson bracket, and then we have a way of constructing incompatible measurements, and then CM plus is just as effective as quantum mechanics for describing any given experiment. And so again, there's no need to distinguish between an object being classical or quantum because we can describe both in both ways. So I presume that many of you have seen the cartoons that have as their punchline, correlation is not equal to causality. But I think that suggests that we might at least ask, well, what do we have to add to correlation to give us causality as well? So one answer is given by a literature in philosophy literature called causal modeling, which adds the idea of interventions, in which what they say is, well, we'll write the probability that y equals y, given that we've turned a dial so that x is equal to x. So it's rather different from the ordinary sort of probability thing because there's an action involved, an intervention involved. And we can use that as a way to discuss transformations of an apparatus. And causal modeling introduces a whole graphical and logical tools on top of classical mechanics, classical modeling, in order to do this. It's rather artificial, in my opinion. So we can almost write, rather glibly, however, correlations plus interventions equals causality. But the Poisson bracket in classical mechanics in CM plus gives us an algebra of transformations that can model interventions in an intrinsic and classically natural way, just the same way as the mathematics of quantum mechanics. So we can write down this formalism from causal modeling in terms of the quantum mechanical formalism, or indeed the CM plus formalism, because it is also a Hilbert space formalism. Now, intervention is what people do. That's how we get involved, how we get our fingers into an experiment. We don't get involved on the microsecond by microsecond scale, but we do get involved at the design level. Classical mechanics can't model interventions as systematically as CM plus can, because CM plus has all the mathematics available to it, the quantum mechanics has available to it, of non-commutative transformations, and also of Planck's constant scale noise. Okay, so I'm going to move to quantum and quantum non-demolition fields, because I think it's important for us to gradually, over the course of the next 5-10 years, to become comfortable with quantum field theory as a way to work with signal analysis in a relatively sophisticated way, but specifically for noisy signals, in which the noise is both quantum and thermal. And we need to distinguish between those noises and understand the ways in which those two noises interact with the experiment we're running. So I'm going to assume that measurement results are noisy at all scales. Even if we're talking about 10 to the minus 100 meters, there might be noise there. There might not, in which case, well, that's nice. It makes life easier, perhaps. But zero variance for noise is not a big deal. We can certainly introduce something that does that. But for this to work, I think we have to understand renormalization rather better than we do at the moment. I think we need better mathematical control of interacting quantum field theory. And I'm going to show you how I think that can be done. So if we have an F measurement and a G measurement, and again, remember that these are window functions that describe what the measurements we're using do, how they're different from just measuring at a point or measuring something in a much larger region. Then the averages will be 0 for the free field vacuum state. And I'm going to define this object here as a resonance functional. And actually, it's called usually a vacuum expectation value, but I'm going to call it a resonance functional because resonance, I think, is quite a good way to discuss these kinds of things. Now, because of my finger trouble at the beginning, I'm not going to say anything about this except to say that if you see an asterisk for complex conjugation in anything in the following, assume that it's not really all that important. So we can also calculate higher degree resonance functions for a free field, such as for 4 measurements, just by summing all products of pairwise resonance functionals. So we end up with something like this. So knowing the resonance functional for just 2 measurements allows us, for a free field, to know what the resonance functional for arbitrary numbers of measurements will be. Free fields are very simple, and hence we can do something with them mathematically. So to go back to the signal analysis kind of thing, what I suggest is that we can think of the vacuum state of a quantum or a quantum non-demolition field as a broadband, noisy carrier signal. This is not a pure single wavelength carrier signal like you have in a radio station, but it's something rather more sophisticated. It's broadband, many different frequencies with not a coherent phase relationships between them, but we're talking about probabilistic modulations of measurement results. So here, for the free field in the vacuum state, the distribution for any measurement, any F measurement, is always going to be a normal distribution, a Gaussian distribution, and so the Fourier transform of that is always going to be also a Gaussian expression. But we can use a G measurement operation, exponentiated and bracketed around the generating functional we just used, to construct what we call a coherent modulation. So all we've done is, by using this construction, we've moved the probability distribution to one side. But we can do more than that, because we can modulate the probability distributions, not just where the probability distribution is, but also more details of it. So we have once raised modulation, which you would call a one particle state, in which the probability distribution has been made into this 2 humps instead of the 1. So this, excuse me, word just evaded me. The resonance functional, together with the complex conjugate, determines all the geometric structure of a free quantum or quantum non-demolition field. And 2 slides time, I'm going to talk about this, which I'm going to call a super characteristic function, because if these F measurements all commute with each other, then it gives us a probability distribution, in which case it's a characteristic function. But if they don't commute, then we get something more like a Wigner function, and so it wouldn't be appropriate to call it a characteristic function. Finally, all of what I've done here is all local measurements. If we want to have a global properties, discuss those, then we need global tools, and that will have rather different properties from what I've been discussing. So suppose we do F measurements over here, which turn out to have more or less 0 averages, and over here, 0 averages again, but also over here, we find that it's been displaced a little. So this is just like an ordinary classical field. But if we look in more detail, we find that the statistics over here are very different from the statistics over here, and the statistics over here are just a coherent state. So the task, the engineering task for nanotechnology and for any experiment is to modulate those probability distributions from place to place in a very controlled way, using whatever hardware we have available to us. And of course, these ideal measurements don't exist. We can't measure the electromagnetic field in a cube that's 10 to the minus 30 meters across. But what we can do is we can put a huge, great thing, an avalanche photodiode in the way, and we can record the avalanche events at megahertz rates. And if we do enough statistics with that, we can hope to find some information that would allow us to tell us what the measurement results would be if we had these ideal measurement apparatus. And we can also, to narrow things down much better, we can use many APDs and compute signals or cross-correlation functions. And because there's more information, that will give us more information about what the state is of the things that are happening, whatever it is that is contained by the apparatus. So for a Gaussian state, as I said, for a single measurement, we have a Gaussian probability distribution, a normal distribution. If we do many measurements, then this expression, when we calculate out what it is for the free field, we find that it has 2 terms. It has a noise term, a pure noise term, which is exactly, it corresponds to this. But it also has a non-commutativity term in here. And this obviously, if this is only going to be non-zero, if some of these are at time-like separation from each other. This is going too fast, I know. Hopefully, you will get some sense of how this is working. In a few years' time, hopefully it will be common knowledge. But as well as the algebraic structure, we have to fix the geometric structure. And there are multiple ways to do it. So for the Klein-Gordon field, we have that we go for the wave number components here and for G as well. And we project to the forward mass shell. And similarly, and I won't go through this for time, we can project to the forward light cone for quantum optics. And both of these are positive semi-definite, and they're both manifestly Poincare invariant, so they both give us a full-blooded quantum field theory, free field theory. But if we remove the theta k0 in these 2 places, that gives us a Gaussian quantum non-demolition field with an h-bar scale noise. So this isn't thermal noise, this is real quantum fluctuations. It looks really very close. And what this removing theta k0 from here does is it makes this non-commutativity term 0. It makes there be no commutation relation, no non-trivial commutation relations at all. So very quickly, to show you what the relationship between quantum optics and quantum non-demolition optics is, I'm going to show you how we can construct an F measurement in terms of lowering and raising operators, satisfying this commutation relationship in terms of the resonance functional we had before, and of course with the lowering operator annihilating the vacuum. And that gives us this, this commutation relation, which is the same as was actually in the previous slide. And for quantum optics, we can find an evolution for which this expression is satisfied for any test functions. And that allows us to construct a quantum non-demolition field, F measurements, by using this bullet operation, so that we have a trivial commutation relation for any F and G. And so that generates a quantum non-demolition optics field. And it gives us a commutative algebra of non-demolition measurements, which is a terminology I should have said earlier that comes from quantum commutation. And it just means everything commutes. Everything looks kind of classical. And also the Hilbert space is isomorphic to what we had for quantum optics, because we used exactly the same raising operators in exactly the same vacuum state. And so we obtained the same Hilbert space. But the algebra generated by the QNDF measurements is not isomorphic to that of the F measurements, because of course this is not the same as this. But if we're willing to introduce the Poisson bracket, or if we're willing to introduce the raising and lowering operators, or with vacuum projection operator, any of those three methods, we can model with quantum optics anything that can be modeled with quantum optics. We can also model with QND optics. Now, there's a tricky business here, and that is that the bullet operation for quantum optics, what we do is we project to the two different holistic components, and for one of the holistic components, we change its relationship by changing the sign of K here. That construction is Lorentz invariant, but it's not translation invariant or local. And so there's something tricky here that honestly I do not understand myself. But nonetheless, quantum optics and QND optics are both Poincare invariant, and so they're both perfectly reasonable physical theories. So much too little time really left to discuss in any detail what I think is really the most interesting part of this in many ways, and that is that we can think about renormalization as in terms of a nonlinearity. In signal analysis, think of f of x as a modulation function, and f comma g, the resonance functional, as a resonance, then it's really not obvious that that construction should be linear, whereas it is axiomatically linear in quantum field theory, and I won't go through that for time. So it's obvious to me, at least in signal analysis, but it's really not so obvious if you're talking about renormalization, where for 75 years, no one has said, oh, maybe the nonlinearity is here in this kind of way. But to support this, nonlinearity does appear in real space renormalization, because if we suppose that f of x is a modulation function associated with this square region, and we split it into 9 different pieces, and for each of those 9 pieces, we decide whether or not the result of measuring it is positive or negative, and then we decide whether the sum of all those numbers is either positive or negative, and that's what this expression does, then we obtain this, what we could call a majority rule F measurement. So it's still a measurement, still something that quantum field theory could think of as one of its own. And so there's a nonlinearity there. And so I suggest we should allow and expect that F measurement to be nonlinear. Now I'm really running up against time. So I'm going to skip this, except to say that this more complicated argument comes to the same end result. We should expect nonlinearity. So the Riesz-Schleider theorem in quantum field theory, axiomatic quantum field theory, says that if we have local operators, we can construct any state just using those. We don't need to consider what's happening outside of those local operators. So whereas for the Feynman diagram sort of approach of loop diagrams, loop integrals, where we do introduce stuff that happens in between the regions that we're concerned with, any physics that kind of path integral can approximate can also be approximated by looking at the functions f1, f2, f3, and f4, and constructing nonlinear fragments, as I call them, and considering what the resonance functionals are for each of those. And that we can think of as an inverse problem. Now, I really don't think this is the last word. I think much better mathematics can be done. I think this looks rather like epicycles to me, but nonetheless, it is well-defined mathematics. It gives us a new starting point for how to think about quantum field theory in a way that doesn't, hopefully will not confuse. So I'm not going to go through this, except to say nonlinearity solves all problems. Perhaps not. So I'll just go this last one thing to say that for nanotechnology, nothing changes right now. This really is a futures thing. This is not something that you're going to be using next week. But I think our intuition can start to meld and switch between quantum and classical thinking in new ways. We can still use quantization and the correspondence principle, but we don't have to because we have this new mathematics. We can still say there is a quantum to classical transition, but we don't have to because we have this new mathematics. And as you've seen, I'm now on 32 of 32, and I will stop. Goodness. As I say, very much less applied than I think most of your talks are. But hopefully applicable to nanotechnology in the long term, in the sort of 5 year to 10 years time scale, and to know that this kind of thing might be coming down the pike now rather than knowing about it in 3 years time might be good for you. Or else it will fall under a bus and you will never hear about it again, which is does happen for this kind of research quite often, of course. So if anyone has any questions, I will be glad to answer them.
Yes. Okay. So thank you very much, Peter, for your engaging talk on nanotechnology, not classical or quantum, but both. Your insights have given us a better understanding of this exciting field. Well, just a quick recap. Mr. Morgan explained how nanotechnology combines classical and quantum mechanics. He discussed noisy signals, events, and data, and how we can analyze them. He also talked about the measurement problem and why it's challenging to measure things accurately in the quantum world. Additionally, for the audience, Mr. Morgan introduced us the concept of quantum fields and how they can be studied using signal analysis approach. He also highlighted the importance of modulation and measurement techniques in understanding these fields. In recent decades, quantum and classical concepts have been coming together in various ways. While nanotechnology remains unchanged for now, we can begin to blend and switch between quantum and classical thinking in fresh and innovative ways, expanding our intuition in this field. So let us now move on, yes, to our second Q&A portion. We invite Peter to join us in answering the questions from our participants. Also to our participants, if you have any questions for Peter, please use the raise hand button, or you may send in your questions in the chat box.
So I will say that that was a beautiful summary. I couldn't have done it better myself. Thank you.
Thank you, Peter. So do we have questions from the audience? Maybe I'll start. So Peter, how does the convergence of quantum and classical mechanics in nanotechnology could impact our daily lives? And can you provide some practical examples?
One thing I think is that it's quite frustrating for me to look at what appears in the journals where people are continually trying to prove that quantum mechanics is better than classical mechanics. A lot of time is, may I say, wasted trying to do that. Whereas if you say, well, we're just actually going to use there's a term in philosophy for this. You have a straw man argument. You're telling us that classical mechanics is not as good as quantum mechanics, and it's because you've tied its hands behind its back. Of course you can beat classical mechanics. Can you beat classical mechanics that has had its hands untied? And so that means that you can direct your attention to actually doing the nanotechnology and not worry so much about the technical details of how good one thing is relative to another. That's my take on it, at least.
Thank you, Peter.
Hey.
Well, I see that there are also some physicists here in the group. I also see Sir Peter, John Albert Banay. Do you have questions, sir? Or you have some insights to add?
Now's the time. Well, we're coming towards the time because of my ineptitude with getting the screen share up. I will add, I suppose, that no, I won't. It would take too long. Hi, Ryan.
Hello, Peter. Thank you so much for your time. And maybe, yeah, for the benefits of those students who are very very interested in nanotech and quantum technology. So can you differentiate us? What is the difference between classical mechanics and quantum mechanics? Maybe, yeah, that will somehow lighten the
Well,
the
of
very
course,
abstract, yeah.
but of course, everybody says classical and quantum are completely different. But I personally have found it very productive to think in terms of signal analysis, because there you're not trying to assign particle properties. You're just analyzing the signals. And going down the road, we are going to be doing more big data applications. The data is going to be sampled at the gigahertz scale. Instead of sampling event rates, we are going to be sampling the signal out of the apparatus. And if you're doing that, if you're thinking in signal analysis terms, then particle properties become irrelevant, or can be irrelevant. Again, you can think in terms of particle properties. It will give you a different perspective. But of course, whenever you talk about particle properties, you get into these problems with logic. With signal analysis, I find there's much less problem with that. Perhaps my standards are low. This is what I often say. So I'm satisfied with what this gives me. Other people with much higher standards may feel that it doesn't help them at all. But then they'll have to find their own ways of getting happy.
Okay, I see. So yeah, maybe when we talk about classical and quantum, maybe yeah, we can consider about the scale. So classical mechanics, I believe, yeah, we are dealing with macroscopic objects. Whereas in quantum mechanics, the scale is different. Maybe we are talking about, let's say, behavior of particles, such as electrons, protons, protons or photons. So yeah, the scale is very different. And in this case, maybe also talk about determinism or probability. So for classics, classical mechanics, yeah, we are very, I think you're very familiar with Newton's law. But in quantum field now, quantum mechanics, we are dealing with, let's say, probability of electrons can be found here or there. Also, we cannot deny the fact that we should also talk about wave-particle duality of, let's say, light, nature of matter. So is it light? Is it a particle? Is it a wave? So in quantum mechanics, yeah, the wave maybe, yeah, wave.
There are many questions here, many things. We have -1 minute, but very quickly. For one thing, the difference of scale is determined by Planck's constant. So it's not a length. It's not whether something's small or not. It's whether the action involved in what we're doing is comparable to the Planck scale. And in my perspective, the field theoretic perspective, in which there are no particles, there's just the field and measurements of the field, the action is a scale of a noise. And usually people say, well, quantum noise is different from thermal noise. Indeed, it's not a noise at all.
Okay.
But because we have this CM plus way of thinking about things as well, we can think about quantum noise being a noise very similarly to the way that classical mechanic thermal noise is. The mathematics lets us start talking in different ways about noise, because there are these two different kinds of noise. There's the Poincare invariant noise, and there's the not Poincare invariant noise, which is the thermal noise. So I've certainly seen people at Yale, someone in particular at Yale, say that what we're doing when we do nanotechnology, we are engineering the noise. So nanotechnology becomes, how do you engineer the noise to be just what you want it to be? Because you can't make it disappear, but you can hopefully make it be just exactly what you want it to be. Yeah, in some sense. And because in what sense you mean that can be a very wide conversation, because there can be different ways in which you say, I've got control of my noise, but it's still noise. In some ways, it's not under control, but in some ways it is. And so you're trying to dance around different ways of talking about noise and find a way in which it does something useful. I mean, I want to be an engineer. I'm not an engineer. I'm very jealous of people who are good engineers, but this, I think, can be used as an engineering perspective, which is why I wanted to give this talk. I'm very thankful for you having invited me.
Thank you so much. Yeah, that is why in
Actually,
for the quantum world, so as much as possible we are minimizing the thermal noise, right? So we are doing it
Right, but think
as
of
much
it,
as possible cryo system, something like that.
something I've suggested to
vacuum.
people here is that instead of trying to control the thermal noise and leave it and make it minimal, instead use the thermal noise as a computational resource.
Oh, I see.
Just because after all, you have these two different noises. One is thermal and one is Poincare. The Poincare noise has the advantage that Planck's constant is constant. It doesn't change. Whereas in order to control the thermal state of something large to within, say, 1,000th of a degree Celsius, that would be difficult. But on the other hand, for something very small, for something at the nanoscale, controlling the temperature to 5 significant digits might not be so hard. And if you can get enough accuracy for that, then you can use that as a computation resource. So now you don't have to work at 0 Kelvin. You can work at 300 Kelvin because you're making sure the nanotechnology is at 300.00000 Kelvin. Yeah, not necessarily easy, but a different way to think about this, yes?
Maybe it's more practical, I think.
Maybe.
Accepting the noise rather than avoiding it, because in that case you'll be using a lot of energy to just removing the noise. So how can we take advantage of this noise and just make it a constant? I think might be much practical.
Well,
Very,
hopefully
very
a good
interesting.
engineer will be able to make something of it, yes.
But how? Yeah. That
Yes,
would be,
yes. But
that would be
how?
another question. Yeah.
Yeah, as I said, nothing in my talk is in the next 6 months, year, 5 years, maybe 10 years, who knows? But that's the nature of this kind of research, of course, and you never know whether it's going to come to anything. Or someone else will do it just so much better that one will never be heard of again. That's the other possibility.
Thank you so much, Peter.
Hey, thank you.
So if
So
you
I'm
have
looking
any more questions, if
we
you have
actually
any
a
more
question
questions
from the audience. We have here, good morning. How can the next generation APD, or this is the avalanche photodiodes, can enhance the imaging technologies such as PET imaging or in nuclear medicine?
Well, of course, by focusing on an experiment from 1990s, an APD back then was leading edge, because this is Vienna. They have things on the shelf that most universities can only dream of being able to purchase. But still, what we now have, indeed, you're working with squids rather than with APDs. You're looking at the ways in which the current through a squid changes. I don't see, however, there being any difference fundamentally, in the sense there's always going to be a discrete jump or a drop to a different level, and you register the time at which that happens and you do statistics with that. But I do see that as being quite different from the big data approach of measuring the voltage picosecond by picosecond or whatever, converting it to digital and storing that. I mean, that's 1,000,000 times more data. The processing involved is you're doing the processing in software instead of using the hardware apparatus to do the extraction of the features of the signal, which can be better to do, but you need big computing to do that. And it's not clear to me what the advantages will be, but you do see it happening already, because when you look at the stuff that's done in in the gravitational wave detections, there you do see the signal as it comes in, as it's recorded, and it's much more qualitative. There is something happening for that kind of measurement, even though it's a quantum mechanical device, at our end at least. So 8 minutes past 11. So
Yeah. Thank you so much, Peter.
Thank you. So I
Very
look forward to the next speaker.
So we would like to show our appreciation to Mr. Peter Morgan, who made the time today to join us in this webinar. So this certificate of appreciation is presented to Peter Morgan. We have the certificate on screen for sharing his time and expertise as a distinguished speaker for the webinar series on nanotechnology, empowering young Filipino researchers for an emerging technology-ready Philippines. Given the 7th day of July 2023, signed by Dr. Ryan D. Corpus, S&P Fellow from USDP Shared and organizer of NanoHubs program, and Ms. Edna Nashanseno, Division Chief of Emerging Technology Development Division of USDP Shared. Before we proceed to our next speaker, we'll have a photo opportunity with Peter. May I ask all participants to please open your camera. Okay, in 3, 2, 1. And then the next pages. Three, two, one. I think that's it. Thank you again, Peter, for sharing your knowledge and making nanotechnology more accessible to us. We appreciate your insights and look forward to exploring this fascinating field further. Thank you so much.
Thank you.
Honored to have you, Peter. Thank you so much. Thank you so much.